पुरुषस्य रूपमधिकम् प्रच्छन्नगुप्तं धनम् विद्या भोगकरी यशः सुखकरी विद्या गुरुणा गुरुः विद्या बन्धुजनो विदेशगमने विद्या परं दैवतम् विद्या राजसु पूज्यते न तु धनम् विद्या विहीनः पशुः विद्या प्रशस्यते लोकैः विद्या सर्वत्र गौरवा विद्यया लभते सर्वम् विद्वान् सर्वत्र पूज्यते ज्ञानेन सदृशं पवित्रमिह विद्यते न हि ज्ञानेन सदृशं पवित्रमिह विद्यते न हि ज्ञानेन सदृशं पवित्रमिह विद्यते।
Dr.Santosh Waghu Zote has completed his B.Sc in Chemistry at Sathaye College, Parle, Mumbai in 2005. He continued his studies at the University Department of Chemistry, the University of Mumbai, earning an M.Sc degree in Organic Chemistry in the year 2007. He has cleared Maharashtra's state eligibility test for lectureship. He completed his Ph.D. from the same esteemed institution. The doctoral thesis, titled Studies in Design and Synthesis of Organofluorine Liquid Crystals, was conducted under the guidance of Professor M.M.V. Ramana. During his Ph.D., he was awarded the Departmental Research Fellowship by the Department of Chemistry, University of Mumbai, Junior and Senior Research Fellowship, that is, the JRF and SRF of the UGC for the meritorious students under the UPE Green Technology Program. Dr. Zote currently serves as an assistant professor in chemistry at Sathaye College Autonomous, Parle since December 2013. His experience extends to VPM's R.Z. Shah College in Mulund, where he worked as an assistant professor in chemistry from July 2011 to December 2013. Earlier in his career, Dr. Zote gained practical insights as a research and development chemist at Mode Pro Private Limited at Juinagar in Navi Mumbai. While working in Sathaye College Autonomous, he has also worked as an assistant coordinator for IGNOU Study Center 1603 from January 2018 to December 2023. Dr. Zote is a recognized research guide of the University of Mumbai for M.Sc, M.Sc by research, and Ph.D. students specializing in organic chemistry. His journey has taken him to several institutions, including the Institute of Science, Fort, Dapoli, Ratnagiri Sub-Center, the University of Mumbai, the UGC Staff Academic College, the University of Mumbai, wherein he served not only as a resource person but also a guest speaker. Dr. Zote has actively participated in workshops on intellectual property rights as well as served as an observer for entrance examinations such as NEET and the UGC NET, CSIR, JRF, CUET. His research has led to numerous publications in scientific journals like Web of Science and Scopus, covering topics like liquid crystals, green synthesis of nanoparticles, docking, etc. Dr. Zote has presented his research work at various national and international conferences throughout the country. Additionally, Dr. Zote has published various chapters in an edited book and authored a book titled General Chemistry 1. Let's welcome Vidyvchspati, Dr. Santosh Zote.
Namaste. My name is Dr. Santosh Waghu Zote. Today I'll be speaking on my doctoral work on studies in design and synthesis of organofluorine liquid crystals. I submitted the thesis to University of Mumbai under the guidance of Professor M.M.V. Ramana, Department of Chemistry, University of Mumbai. It was submitted in June 2014. While understanding liquid crystals, let's go back to history of the liquid crystals, where it all began. It began in the year 1888. The Australian botanist and chemist Friedrich Rindzer, while studying cholesterol benzoate, he found out some unusual phenomena occurring with the molecule. So he wrote the letter to Otto Lehmann, who is a German physicist. Using the microscope, Otto Lehmann was able to find out what type of phenomena is occurring, and he mentioned them as a liquid crystals. So from 1888 till nowadays, liquid crystals are being in huge demand. As I said, this phenomena was discovered in 1888. We all are very much aware about the states of matter like solid, liquid, gaseous, plasma. Over here I am just highlighting on the phase, that is liquid crystal. It is in between solid and liquid. Solid has particular orientation, fixed shape, whereas liquid, that position order and the molecular forces are different. In gases there is no ordering and no molecular forces. Well, our topic for understanding is not solid, liquid or gases. We are going to focus on liquid crystals. So let's move on. What is liquid crystals? So the diagram over here that displays the solid, liquid crystals and liquid. If you could see, liquid crystals, they are having some regular pattern or some regular alignment as displayed over here in the image, but slight orientation is different. So they have lost the orientation, and if you compare that with the liquid, there is no orientation and no regular pattern. So this is a difference between the liquid crystal and liquid. Ideally, solid on heating should pass to a liquid phase, but in the case of the compounds which are liquid crystals, they pass from liquid crystal to liquid. Means what? There is an intermediate phase of liquid crystal. So closely identifying this, as I said even earlier, liquid crystals maintain some orientations or some ordering, but liquid do not possess the same. Liquid crystal can take the shape like a liquid, but they still contain the rigidity of the solids. Understanding more about liquid crystals, while heating, a solid goes into a opalescent fluid. We call it as a cloudy or milky white, milky substance. Then it goes into a isotropic liquid, that is a clear liquid. And exactly opposite occurs for cooling. From isotropic it goes to opalescent fluid, and then from opalescent fluid it goes back to solid. We will now understand types of liquid crystals. Thermotropic liquid crystals and lyotropic liquid crystals. As the term itself says, thermotropic means based on the temperature. This liquid crystals changes the phases or changes the textures based on the temperature. As we increase the temperature, the phases will change. The another type, as I said, lyotropic. Those are depending on the concentration. So the concentration, if it's varied, the texture will vary, it will change. So it's about lyotropic liquid crystals. Understanding the various phases of liquid crystals. Very commonly known phases are nematic liquid crystal, smectic liquid crystals, cholistic liquid crystals, discotic liquid crystals. Let's try to understand each in a brief. Nematic liquid crystal. The nematic term is mentioned as a thread-like. In Greek, it is said to be a thread-like. If you could see the structures over here, there are long chains of carbons, means a thread-like. Long chains, thread is displayed over here. So, a filament or tail type of thing is there towards the terminal. And some hardcore benzene rings are kept as a core. So, in this you can see, as liquid crystals are combination of solids and liquid properties, the hardcore, that is the structure of benzene, naphthalene, they are forming the core. They represent as a solid part, and the filaments, the long chains, the alkyl groups, they behave like a, you say, the tail of fluid part. This is the smectic liquid crystals and cholistic liquid crystals. Cholistic liquid crystals are basically the same liquid crystals, but they contain a chiral carbon, or basically we can say chiral nematic phase or chiral nematic liquid crystals. Smectic liquid crystal has a different class, smectic A, smectic B, smectic C. We are not going in detail about that. Smectic A, B, C, these all are depending on the different types of angles, the orientation that the molecule is obtaining. For the discotic, the structure displays like a disc over here. You can see some discs are displayed along with the tail. You could see over here also, the core is mentioned of benzene, multiple benzene rings are there linked together, and this ring forms a hard core, and then R group are the alkyl chains, the tailing or the fluidity producing part. This is all about discotic. Now about characterization of liquid crystals. How do we characterize the compound is liquid crystal or not? There are techniques commonly used, that is using polarizing optical microscope with a hot stage and with this attached to the PC. Means the software is there which generates the data, which monitors the hitting rate, which displays the image as shown over here as a texture. This is a texture of smectic phase. Smectic phase is coming after nematic phase. It is not necessary that each compound will have all the phases. Compound might have only nematic phase, it might only have smectic phase, it might have more than one phase. So this depends on the core of that particular compound. Further, additional instrument is DSC, differential scanning calorimetry. It helps to identify the phase transition, what type of changes are occurring in the particular molecule on heating. You could see over here DSC, differential scanning calorimetry, which is one of the most important instrument for analysis of this liquid crystals, along with polarizing optical microscope. If you see in the thermogram of this particular example, there are endothermic peaks as well as exothermic peaks, means while heating and while cooling the peaks are obtained. This says that there are some transition occurring with the molecule which you can study with the help of DSC, and during the same temperature you have to take down the texture on POM. So with DSC we found out the range when we should take the temperature images of the particular compound. So as I told you about liquid crystals, let us discuss why we are interested in liquid crystals. It is due to the applications of liquid crystals. You could see numerous applications and still it is going on. LCD screens, LCD thermometers. Basically liquid crystal thermometers are those thermometers which will replace mercury in the coming days, because mercury is an hazardous chemical. So these thermometers can be utilized. Body imaging applications, it has a medical applications, mood ring, battery charge indicators, chromatographic, organic synthesis. Organic synthesis as a solvent they are used. In chromatography they are used for separation of particular compounds. In spectroscopic techniques they are used. So there are varied applications of liquid crystals that fascinated us to take the work. So now we are moving ahead, understanding the work on liquid crystals. For continuing the work on liquid crystals, we began with referencing. As always, each research has to be done by referencing. So when I did my PhD, that time we started with offline referencing, visiting the libraries. We visited IIT, ICT, universities library, which has a thesis section wherein a large number of chemical abstracts are kept, which we manually visited, taken down the notes, and after a few months we had the access to SciFinder, that is online referencing facilities. SciFinder provided us additional information as compared to the manual referencing. Apart from abstracts and details, it gave more data. It also gave us the predicted properties. We got to log in into the server. We had the login credentials. We logged onto the website. Then we could do complicated research. The structure is shown to find out that you can easily find out the references for such a complicated structure using online facilities like SciFinder. This not only gave the detail about the experiments or the paper, it also gave experimental properties. Some predicted properties were also given by the SciFinder. So based on the referencing, what we understand, these are the certain molecules which are showing liquid crystalline properties, like one hand having azo, and again diphenyl rings with long chains. Again over here a bigger structure. The next part is again containing fluorine. So such structures are required for a compound to be liquid crystal or to show that required properties. Similar structures are available in the literature. Number of rings are more, say 6 rings over there, and then second structure there are number of fluorine atoms, around more than 12 to 15 fluorine atoms are required to generate a liquid crystalline structure. So ideally one can understand that the length to breadth ratio has to be high and there has to be a presence of dipole moment. So these are certain parameters which we thought of to be incorporated in our studies, but these structures are very complicated and perhaps difficult to synthesize. So we thought of preparing structures with simple structure and exhibiting the similar properties. These are a few examples which are as a part of core that can be kept to produce the solidity or crystallinity to the molecule. Let's come on to the criteria for a molecule to be liquid crystalline. As we see in the structures which are having length to width ratio higher, means long structures, they have the capacity to be liquid crystal. And one of the more important parameters is the presence of dipole moment. So sticking to these two parameters, we try to synthesize liquid crystals, but these theories like presence of dipole moment and high length to width ratio are not sufficiently precise. They are relating to the structures. Why do I say this? Look at the structure. This structure was prepared as a liquid crystal, means possibility to be a liquid crystalline compound. Diphenyl compounds, 4 benzene rings are there, long chains are there, alkyl chains, both end alkyl chains are kept in all the structures with fluorine atoms. Still these compounds are not liquid crystals. They are normal organic compounds. So we cannot make a generalized statement that it is the presence of length to width ratio, the compound can be liquid crystal, or having dipole, the compound can be liquid crystal. As we have seen in this case, the compound contains length to width ratio as a high and also the dipole moment high because of fluorine, but still this compound is not a liquid crystal. So as discussed, based on the literature referencing, we began our designing and synthesis of liquid crystals. Taking this designing part, I mentioned over here high length to breadth ratio and dipole moment. We are going ahead in the synthesis of our liquid crystalline compound. First scheme, we are selecting fluorinated, as we know the topic, it is synthesis of organofluorine liquid crystals, means fluorine is present in the organic molecule. Why do we select fluorine molecule? The reason over here is displayed over. You can see fluorine is highly electronegative element. It has good dipole moment, and the highest strength of CX bond is mentioned in this chart. 3.98 is the highest electronegativity of the halogen atom. And if you could compare the size with hydrogen, it is having almost similar size, so it is easy in terms of space or replacement or as a structure. So we stick with, we try to go with fluorine. And the examples, as I quoted earlier, few reported compounds containing fluorine are liquid crystalline. So we further started our work in which gave us a scope to go for fluorinated compounds. Here, as I said, the challenges are there. What challenges are there in preparing liquid crystals? Ideally, as per the reference, 0.5% organic compounds are liquid crystals. So the probability of organic liquid crystals is very less. So itself it is challenging, and it requires long alkyl chain. And as I said, we'll be introducing fluorine. Introducing fluorine is not easy in organic molecules because handling fluorine is difficult. So we got to find out various other means to introduce fluorine into the organic molecule. So these were the challenges. Synthesis, we began with the compound which was first the reason for liquid crystal, that is cholesterol benzoate. Friedrich Rinzer in 1888 used cholesterol benzoate. We began with similar derivatives so that the possibility of obtaining the properties are higher. In this case, the scheme is, in this we have done the esterification, wherein para-nitrobenzoic acid is esterified using DCC and DMAP, and we get the compound 3, that is nitro derivative of cholesterol benzoate. This cholesterol derivative is further reduced using tin to amino derivative. The most important part to note down over here is the amino derivative is already reported as a liquid crystal. So why have we prepared this content? Why have we preparing this compound? The reason was this compound, although reported liquid crystal, it is undergoing decomposition. So it is of no value if the compound undergoes decomposition. So what is our contribution to this? We try to modify this compound by introducing fluorine, and in the next step, if you could see, this fluorine is incorporated in the form of trifluoroacetic anhydride, that is acyl group, CF3. 3 atoms of fluorine are introduced, and this compound, when analyzed, investigated using POM, that is polarizing optical microscope, and DSC, it was found to be liquid crystalline. And we are happy to mention that this compound did not undergo decomposition. These are the DSC of the particular compound, which is mentioning that it is a liquid crystal. This is a polarizing optical microscope or the texture of the particular compound. This is a nematic phase. Images are taken while heating. This particular compound is ideally a chiral nematic because cholesterol is a chiral compound. So this falls to a category of nematic but chiral nematic. For the first scheme, conclusion is that for the first time 2,2,2 trifluoroacetamido group is involving as a liquid crystalline unit. These are the various schemes which we devise in our work. As the fluorine is having influence and the long chains are required, we try to synthesize this compound as a simple compound, as our aim is to simplify the compounds. So we went for this particular simple compounds, but we could not get the required properties. So these compounds which were synthesized were non-mesomorphic in nature. So we thought that mere presence of long alkyl chain in fluorine is not essential. Some more characteristics are to be involved in this particular schemes. So for that we meant for the ionic to increase more polarity or more dipole, we added a contribution from an acid part, that is HbF4 fluoroboric acid, as a salt with the amines, and these compounds are found to be liquid crystalline. Why we selected fluoroboric acid? Because one of the strongest acid. In this chart, various acids are displayed. Some of the acids myself used for this particular work, some of the acids my colleagues, my friends are used in their research work. I had focused on fluoroboric acid, triflic acid, that is CF3SO3H, and trifluoroacetic acid. Various series of the compounds are synthesized. The data is displayed over here, POM images, next scheme similarly based on this. So all this data was very positive for us, and the use of fluoroboric acid generated the compounds to be liquid crystalline. However, the issue was that these compounds had high melting points and high clearing points. So to lower the clearing point, we began a work. These are the images of the compound synthesized. These are optical micrographs which shows the positive results. So as I mentioned, the compounds were liquid crystalline but with a higher clearing temperature. So we try to shift from fluoroboric acid and inorganic acid to organic acids, that is a trifluoromethane sulfonic acid. In an attempt for this, in this scheme, we synthesized these compounds were found to be liquid crystalline as per the results. So based on the results, further the scheme was continued and various other compounds were synthesized. These are the data of the transition temperatures depicting that they are liquid crystals. DSC of the synthesized compound, these are showing positive results, having multiple peaks while heating and while cooling. So these are the pure images clearly mentioning the smectic phases displayed on this image. One mentions the oily streak, that is the rare cases which obtains the oily streak. Summary of the scheme, all the compounds were mesomorphic, that is liquid crystalline. Further, we thought of lowering the melting point and the clearing point. So for that, we introduced a weaker acid, that is not triflic acid. We went on to use trifluoroacetic acid. So from triflic, we came to TFA. So in this case, we are using a weaker acid, TFA, just to lower down the clearing temperature. While synthesizing this compound, we noticed that there was a drastic change in the temperature. This compound was liquid. So as it was liquid, we could not identify the liquid crystalline properties of this particular compound. So we further went in the scheme with a longer chain. The images of the DSC and POM, which shows a nematic phase over here. You could see a thermogram having two peaks while heating and cooling. Similar schemes were discussed and carried out with simple smaller molecules using no chain, no alkyl group, additional alkyl group. Some of them are displayed over here. Most of them were non-mesomorphic, because still it is clear that some chain has to be present in a particular molecule to be liquid crystalline. In this particular series, we could not generate all compound to be liquid crystalline. Only one compound in which alkyl group is there, it is mesomorphic. You could see at the above mentioned imidazoline compound, it requires 16 to 18 carbons to get the properties. However, in one of the scheme which we displayed over here, using triflic acid and TFA, both the compounds prepared are having mesomorphic nature without use of a single alkyl group. These are the data thermograms of particular compound synthesized. These are some of the schemes which I discussed with you for liquid crystals that we carried out while functioning in presence or preparation of liquid crystals. So ideally, to conclude, we were able to synthesize liquid crystallized compounds using triflic acid, using TFA, using fluoroboric acid and cholesterol derivatives. So we can see that it is not essential to have longer chains and only dipole moments. It is depending on the ionic nature of the molecules. If there are ionic part, we can say that the ionic part is giving the crystalline nature to the compound, and the filaments, that is the long chain, that can give the fluidity. So based on this, one can synthesize liquid crystals for its varied applications. I like to acknowledge over here my mentor, Professor M.M.V. Ramana sir, Department of Chemistry, University of Mumbai, for giving me the Departmental Research Fellowship, the DRF. I like to thank UGC for Junior Research Fellowship and Senior Research Fellowship under the UGC UP program. I like to thank PTVA, Sathaye College, for providing this platform and the opportunity to share my research work with you, my lab mates, my colleagues and friends, my family members as well. Thank you.
ज्ञानेन सदृशं पवित्रमिह विद्यते नहि ज्ञानेन सदृशं पवित्रमिह विद्यते नहि ज्ञानेन सदृशं पवित्रमिह विद्यते